This is section 11.6, which is phase diagrams. I will explain how they work and then provide a few examples and show how to use them and what you can use them for. So this is a basic phase diagram. This one is not labeled, but most phase diagrams are labeled. However, the basic part of it is that the x-axis is labeled with temperature, the y-axis typically with pressure. As this goes to the right, the temperature is increased. As this one goes up, pressure is increased. There are a couple main parts to the phase diagram. Specifically, there is these three main colors, the yellow, the blue, and the greenish, which this is the gas phase, this is in the liquid phase, this is in the solid phase. This means that when the temperature is this and the pressure is this, if you go where they meet and it's in the solid area, it'll be a solid. This is true for any of the points where the two meet. However, there are the different curves. So this is the sublimation curve, this is the melting curve, and this is the vapor pressure curve. They are always typically the same color. So the green is always the sublimation curve, the blue is the melting, and the red is the vapor pressure. This is where the phase changes are in equilibrium. So at the sublimation curve, sublimation and deposition is occurring in equilibrium, and it's the transfer of phases, pretty much. The phases are changing. There are a couple of main points and stuff surrounding the points that are important. The critical point, which is up here labeled with C, is where the liquid and gas phases are indistinguishable from each other. After it becomes a supercritical fluid. So when the temperature becomes high enough and the pressure becomes high enough, and it's in this area, it is a supercritical fluid, and it's hard to distinguish, indistinguishable. Even the temperature and pressure makes an indistinguishable liquid gas sort of fluid. The normal melting point is the melting point at 1 atm. This is not labeled, so it's not possible to see where 1 atm is, but my next one that I have is labeled. The triple point is where all three phases are in equilibrium. This is labeled here with T, and this is sort of a weird, it's melting and solidifying and evaporating, and everything's happening at once because all those phase changes are occurring. So this is the phase diagram for water, and this one is labeled, so you can see at 1 atm where on the melting curve the normal melting point, which is the melting point at 1 atm, is right here. So it's at 0 degrees Celsius, as we know. Solid water becomes a solid at 0, and it also melts at 0. However, a big thing to understand when it comes to phase diagrams is that it's possible to move from the solid to the liquid to the gas and something like this, because just by adding heat at 1 atm, which you can tell here, this is like solid is an ice becomes water, water becomes water vapor, just by adding heat. There's no change to pressure, and this is possible because those curves are in that alignment. Similarly to how you can add heat and go across, let's say you have a gas and you increase the pressure, it can become a liquid now. That's how you manipulate the phases and phase diagrams to, that's how you use them, pretty much. So for this one, I believe this is the phase diagram of CO2. It's not possible to just add heat to go across at most points, at most points, but also at a pressure of 1 atm. So at atmospheric pressure, you can't just turn from a solid CO2 to a liquid. No matter what temperature you're at, you have to have it be at a different pressure. So that's why CO2 does not have a normal melting point. It has a normal sublimation point because it sublimates from a solid to a gas at 1 atm. So they can come in various different, the curves can be in different spots, meaning that they have different properties to them, but always knowing that you can add heat going across or increase or decrease pressure going up or down to manipulate the phase of something. It's a very important, but I think easy to understand aspect to chemistry.